accurate. What are you doing? You're doing down to the right, like this, and then I start at the middle and do this, like 30 degrees and then 30 degrees. That's what I do. And then just make sure you're, oh, not Y. What is that axis? That's the X, Z, and that's what I do right there. There's actually a drawing tool in OneNote for drawing these axes. I think it's at 45 degrees though, unfortunately. I don't use it. Yeah.
Why isn't that they didn't just keep the XY where it was and just pull it from the back?
Do you remember my answer to that question? Because that's just how it is. It's just how it is. I think the way I think of it as, like, it was X and Y and it went like timber and it fell over. That's all I got. That's all I got. I mean, it does make sense that right is positive, up is positive, and towards you is positive. I totally see what you're saying, but it could have fallen forward. It just is how it is. I mean, I guess another way to think of it too is that if the perspective is here, okay, if you're looking this way, another way to think of it as, if this is positive, if this is like the positive, if you are like standing here, if you're walking forward, like we think of walking forward on the x-axis. It's all I got. It's just how it was decided. We need to unify it. If you start flipping them, we're not gonna follow. It's hard enough as it is, right? Contour diagrams. Now you have seen them before. Where have you seen, besides when I showed you that weather map, where have you seen contour diagrams? You've seen them. They are not new to you. They are definitely not new to you. Not new to you. You've seen them before.
You mean like geometrically or in graphs?
In like real life, like out in the wild. In real life, where have you seen?
Kind of looks like the hockey thing.
So, okay, we're going to turn that into a contour diagram. But where have you seen contour diagrams in real life? What? Mountains, yeah. Topo maps. Have you seen topo maps before? Topological maps?
Wait, those are like...
Yeah, that is a contour. Look, here's a contour map. You've seen things that look like this. What is that? That's a contour map, right? Where's it getting steeper? Well, it looks like it's getting steeper here. Why? Why is it getting steeper there? The contours are what?
Closer together.
They're getting closer together, right? And it gets really, really steep, so maybe that's going up like this. Right? Each of those lines represents a different altitude, right? A different elevation. So this might be, I don't know, 10 feet. This might be 20. This might be 30. This might be 40. This might be 50, 60, and 70, right? Why is it important that they are evenly spaced like that? 10 to 20, 20 to 30, 30 to 40, 40 to 50. Yeah.
Because you need some kind of like...
Say it, yeah.
Axis mark.
Yeah, you need some sort of commonality,
yeah,
right? Well,
then when they get, because the closer they get together, it represents
steepness, exactly. The numbers don't represent the steepness. How the distance the contour lines are from each other represents the steepness, right? What would happen if I just made it 10 and then 12 and then 30? You would look at it and be like, you know how to read that. Like, you've seen that before. It just wouldn't make sense based on how we are set to learn about them. So the key for making contours is evenly spaced altitudes, evenly spaced how high you are from zero, whatever that is. So if you're going over here, when you start making your slices, you slice them evenly. And when you make your slices, imagine you have that big sword. I think I talked to you about it before. I had the big cosplay sword. You are slicing parallel to which plane? Which plane are you slicing parallel to? The XY. The XY, you're slicing this way. So when you slice maybe at this height, you're slicing here, and then what do you end up seeing? This is the part that crossed the function. This is the part that crossed the function. You drop those lines straight down to the XY plane. And then you slice again. You slice again. You slice again. And what do you end up with? What kind of graph? These all go down, straight down, right? And get imprinted onto the XY. So what do you end up with on the XY plane? A bunch of parallel lines like this. Now, why is this accurate? What are some aspects of this contour diagram that tell you that it's accurate? Yeah.
They get bigger and bigger spaced as it gets toward the Y.
Exactly. It's because it's slowing down at the top, right? So what do you know here? That would be steeper, right?
Yeah.
Why do you know it's steeper there? They're what? They're closer together, right? And the only reason you can assume that that's steeper is because we are assuming that each contour line in each different contour line that are parallel is the same distance in terms of altitude change.
So you're cutting it like at just equal distance apart.
Exactly. And if you weren't doing equal distance, this would mean almost nothing to you. How can you tell if something is a plane from a contour diagram? What's the automatic thing? A plane, they'd be what?
They'd be
They'd all be what?
Same distance.
They'd all be the same distance apart. So if I graph something like this, for example, if you saw this, and these were all the same distance apart, what would that be? That would be a plane. But what happens if all of a sudden I put in some more and then like start stretching it a little bit? It'd be wavy, right? It'd be wavy. Now the other thing is, to get any information from this, you would actually have to label some sort of height. So for example, you'd have to say, I don't know, like let's say this is 50. So this would be 40, and this would be 40, this would be 30, this would be 30, this would be 20, 20, 10, and 10, right? Something like that. Because if you don't have the height, what could it represent? A lot of things, right? You just know it gets steeper, but it could be up, it could be down, right? You need those heights. Okay, so when you make these slices and you make these contour diagrams, I could give you a surface like this and say, what does a rough sketch of the contour diagram look like? What are the important things I'm going to ask for or expect? I'm going to expect you to label your axes like y and x, because you could have this shape, but it could be going the opposite way. You could turn it 90 degrees. If you turn this 90 degrees, what would the contour diagram look like? All of these lines would be rotated, horizontal. Exactly. That's what I'm looking for. I'm not looking for hyper accurate, like, oh my gosh, it's half a centimeter away instead of 0.4 centimeters away. That's not what I'm looking for. Or you could start with a surface written as a function. Surface written as a function. Now, here's what you don't do. Don't graph the three-dimensional one to graph a contour diagram. Each contour, all the contour lines, we get from picking a static height and graphing what that height is. The height in this case is not x, it's not y. The height is what? The z. Wiley, you working on math?
Yeah.
Okay, so in this case right here, what you're going to want to do is you're going to start with your your y and your x-axis. You're going to start with your y and your x-axis, and you're going to pick some z-values. Now, the z-values should be evenly spaced. What's a good z-value to start with, do you think?
0.
Let's start with 0. If we start with 0, 0 equals x squared plus 2y squared. If you graph that, that has one solution. What is it? Origin. There it is. How about we pick 1 next? What shape is this? Someone raise their hand and then I'll call on you. You can tell me, what shape is 1 equals x squared plus 2y squared? What shape is that, Chip? Yeah.
Is that a oval?
It's an oval, right. It'd be a circle if the 2 wasn't there and just a 1. So you do your intercepts, right? What's the x-intercept on that? When y is 0, what's x?
1.
Or?
-1.
And what about y? What's the y-intercept on that, everybody? Come on, do the math. What's the y-intercept? Root 1/2, right? Square root of 1/2. So that's less than 1. So it's like this, right? So this right here is when the height is what? 1. What about 2? What happens now? We have x squared plus 2y squared. What happens now? What's the x-intercept? Square root of 2. And what's the y-intercept? 1 or square root of 1. 1 or negative 1, right? So what do you end up with? Another what? Another oval. So what are you going to end up with? A lot of concentric what? A lot of concentric ovals, right? So that's 2, and we'll say that's 3. So from that contour diagram, what would that look like if it was in front of you? If that surface was in front of you, what would that look like? A dome? It starts at 0, 0.
Oh, like the other way.
It's a bowl, right? It's like a bowl, but is it a circular bowl? No, it's like an oval. It's like if you took a bowl and like squished it a little bit, right? So it's this shape going all the way to 0.
Contact lens.
Exactly, yeah. Take a contact lens. I like that. That's good. It's like a bent contact lens. Exactly. Is that a rotational solid? If you were looking at that, is it a rotational solid?
No.
Ain't circles, right? Those aren't circles. If you were to take this radius right here, let's say this was a radius right here, call it R1. If you were to sweep that out, how far is R1 going to go? It's going to go outside around it, right? So is that a rotational solid? No, it's not a rotational solid. If those were circles, would it be a rotational solid? Yeah. So it kind of looks like a rotation, but it's not. So sometimes you'll be given a graph that's nicely printed like that, and then you have to make a rough approximation of the contour diagram, or you might be given an equation and be expected to make a bunch of graphs. What about this one? How about you sketch that contour diagram for me right now? Sketch that for me. Do that. A bunch of concentric circles, right? They're all centered. They all have the same center. What's the key thing you have to make sure you do when you draw these circles, though?
They can't come close to where they are.
They get what?
They get further, like closer together when they're further.
Yeah, as they get bigger, they get what?
Closer.
Closer together. It's kind of hard to draw after a while, right? Now, if I didn't put numbers on those concentric circles, that could be one of two things. That could be going down or up, right? So if you were to do that, you can change it to a different eraser, but it could be like, this one would be like 50, 40, 30, 20, 10.
That's the z value.
Those are the z values, exactly. Those are all of the points on that surface where z is 50, and then 40, and then 30.
And z is
Coming at us.
sticking out.
Coming straight out at us. Exactly. This is y, this is x, and where z is pointing straight at us. Coming out of the board. It's coming straight at us. So if you're looking straight above it, exactly how you view a topo map, you're looking straight down on it. So do you get to have some good practice graphing these? Oh, you'll get to lots of good practice. You'll get to lots of good practice.